Hi everyone. We're going to use the Henderson-Hasselbalch equation in this video to calculate the pH of a buffer. I love the Henderson-Hasselbalch equation. That's the way that I usually calculate the pH of a buffer. Hope you enjoy it. The Henderson-Hasselbalch equation is really easy to derive from the Ka expression. Let me just write down a Ka reaction as a reference here. So we would begin by saying Ka is equal to products over reactants. And then the next thing we would do is take the log of both sides of the equation. But when we take the log of the right-hand side, we're going to remember something that you probably learned in one of your math classes, which is that the log of a product, A times B here, is equal to the sum of the logs. So that would be the log of A plus the log of B. So on the right-hand side here, we're going to treat H plus as A, and then the ratio A minus over HA as B. So here we go. The log of Ka is going to be equal to the log of H plus the log of A minus over HA. And since we're solving for pH, maybe we should subtract the log of H plus from both sides and kind of isolate it. So the negative log of H plus, if I subtract the log of Ka from both sides, equals the negative log of Ka plus the log of A minus over HA. And couldn't I rewrite the negative log of H plus as pH? And couldn't I rewrite the negative log of Ka as pKa plus the log of A minus over HA? This is the Henderson-Hasselbalch equation. And I suppose we could write it in another form if, for example, our buffer contains B and BH plus. That would be the pH equals the pKa plus the log of B over BH plus. And this is the form of the equation that we would use if our buffer contained ammonia and ammonium chloride. Let's look closely at this equation and think about this term in the equation. Let me ask you, what if the concentration of A minus equaled the concentration of HA? That would mean that this ratio equals 1, and the log of 1 is 0. So the pH would just equal the pKa. So what I'm trying to get you to realize here is that this term in the equation is never going to be very large. So you have to remember that when preparing buffers, when you prepare a buffer, you want to choose a weak acid whose pKa is close to the desired pH. For example, if you want to prepare a buffer with a pH of 10 and you choose a weak acid whose pKa is 4, this term in the equation is never ever going to be large enough to get you up to a pH of 10. So keep this in mind when preparing buffers. So let's see if we can use the Henderson-Hasselbalch equation to calculate the pH of this solution. I'm looking at these solutes and I'm thinking that this solute would be B and that this solute would be BH plus. And we're going to have to look up the pKa of this dimethylamine or dimethylammonium in this case. And the pKa is 10.774. So the pH equals the pKa plus the log of B over BH plus, and I should put brackets there for concentrations. So the pH would be 10.774 plus the log of, well, the concentration of B is 0.025 formol over the concentration of BH plus, that's 0.075 formol. And when I did the arithmetic, I got 10.29 with an insignificant 7. I suppose you could call that 10.30. Notice that the pH is close to the pKa, again, because this term in the equation won't ever be very large. And I want to say one more thing about why I really like the Henderson-Hasselbalch equation. We can rewrite this term as the log of this concentration can be written as 0.025 moles of B for every liter of solution. And downstairs we can do the same thing. We can rewrite this term as 0.075 moles of BH plus for every liter of solution. And remember, B and BH plus are in the same solution, so liters cancel. And what that means is we can just use moles in the Henderson-Hasselbalch equation. And that's going to be useful when we start doing buffer interaction problems. So I hope you enjoy using the Henderson-Hasselbalch equation. I sure do, and I use it a lot. Thanks for listening.